Welcome back. Let's learn how to integrate vector-valued functions. Alright, so over the last few lessons, we have looked at how to take the derivative of vector functions as well as some of the uses, but now it's time to take a look at how to integrate vector functions. And remember that integration is also called anti-differentiation, so it is essentially the opposite of taking a derivative or reversing the process of differentiation, right? Integrating and taking a derivative are opposite operations, just like addition and subtraction and multiplication and division. So the integration of vector functions works exactly how you would expect it to based on how we differentiate vector functions. Remember that when we take the derivative of a vector function, we simply take the derivative of each component individually. And so if we want to integrate a vector function, all we have to do is integrate each component individually. And that will be the case for both indefinite and definite integrals of vector functions. But to start, let's just take a look at indefinite integrals. If we have a vector function r of t, which is equal to f of t times I plus g of t times j plus h of t times k, then the indefinite integral of r of t looks like this. The integral of r of t dt is equal to the integral of f of t dt times I plus the integral of g of t dt times j plus the integral of h of t dt times k. Notice that in each case we are integrating a function in terms of t, so we are integrating with respect to t, so we do have dt within each of those integrals, including the integral of r of t. Okay, and so this is the formula or the process that we will use for solving an indefinite integral of a vector function. And just to be clear, in this video, we're just going to focus on the process of integration of these vector functions. We'll talk about the applications in future lessons. All right, but now if you remember, when solving an indefinite integral in Calc 1 and Calc 2, we always needed to include a constant of integration, that plus c that we always put on the end of the answer to our integral. We still need to do that here. In fact, we actually get 3 constants of integration because we have 3 different integrals here, one for each of the components. But there is a way to write that nicely so that we don't have 3 constants of integration. We can represent them with just one constant. And so let me show you what I mean by that. If we were to look at each of these integrals individually, we would have the integral of f of t dt, the integral of g of t dt, and the integral of h of t dt. When we solve each of these indefinite integrals, here's what we will get. Remember that when you integrate a function, you get its antiderivative, which typically we represent by just capitalizing the letter for the function. So for small f of t, the antiderivative or the integral would be capital F of t, but then we would want to include our constant of integration plus c, but now we're going to have 3 of them, so I'm going to give it a subscript of 1. And then for this integral of g of t, the antiderivative would be capital G of t, and then we would add another constant of integration, but this time I'll call it c sub 2. And then finally for h of t, the integral will be capital H of t, and then once again you would add another constant of integration, which I will call c sub 3. All right, so from each of these 3 integrals, you do get a constant of integration, but if we were to put these solutions into their places in the vector function, what we'll be able to do is regroup our terms and find a much easier way to represent that constant rather than having 3 of them like this. All right, so here's what I mean by that. The integral of r of t dt would be equal to capital F of t plus c1 times I, and then we're going to have our j term and our k term. The j term is g of t plus c sub 2, and the k term is h of t plus c sub 3. All right, what we can do here is then distribute I to both of these values, j to both of these values, and k to both of these values, and then regroup all of the terms based on whether they are a function or a constant value. All right, so here's what that looks like. This integral would be equal to f of t times I, and then I'm going to skip the constant term for now. It is multiplied by I, but I'm going to leave that for later. Let's move on to g of t times j. That would be our next term here, capital G of t times j, and then I'm going to move on to capital H of t times k. All right, so we have capital H of t times k. But then we don't want to forget about those constants. We have 3 of them. We'll have c sub 1 times I, c sub 2 times j, and c sub 3 times k. Let's put all of those on the end here. C sub 1 times I plus c sub 2 times j plus c sub 3 times k. What we have here are essentially 2 vectors. One vector whose components are just the antiderivative of the original vector's components, and then another vector whose components are all constants. And so what we can do here is just rewrite this vector with these constant components with vector notation. We can just call it a vector constant of integration and write it as a vector c. Okay, so I'm going to do that in a second, but something else we can do is just rewrite this vector to be the antiderivative of our original vector. What I mean by that is we could say that this is equal to capital R, or a vector capital R of t, plus that vector constant of integration c. All right, that is how we would generally represent the antiderivative or the integral of a vector function. You will get the antiderivative of that vector function, whose components would just be the antiderivative of each of the respective components of the original function, and then you add on a vector constant of integration, whose 3 components are just constants. All right, and so then just like with integrals from Calc 1 or Calc 2, unless we know an initial condition, we can't find the value for this constant of integration. So in most cases, when you solve an indefinite integral of a vector function, this plus vector c will just stay as plus vector c. Okay, and one more thing I want to point out here, I think this might be obvious, but it might be helpful to write this down. Since capital R of t is the antiderivative of small r of t, our original vector function, the following statement would be true. The derivative of capital R of t would be equal to small r of t, our original vector function. Okay, if you take the derivative of the antiderivative, you get back to the original function. So don't forget that that would be the case. This would still be true like it is for regular functions in the past. Okay, so that's how we deal with indefinite integrals of vector functions. But now let's take a look at how we deal with definite integrals of vector functions. And really, it's not all that different compared to indefinite integrals. The only difference is that we now have bounds of integration that we will use to evaluate each antiderivative of each component. All right, so when we have a vector function r of t with those 3 components, f of t, g of t, and h of t, where all 3 of those functions are continuous on an interval from a to b, that is important. These functions do need to be continuous on the interval for which they are going to be integrated on. But assuming that is true, the definite integral of a vector function r of t dt from a to b is equal to each of those components integrated from a to b. Okay, so you integrate f of t from a to b, you integrate g of t from a to b, and you integrate h of t from a to b. It works exactly how you would expect it to based on how we do indefinite integrals. The only difference here is that we now have bounds of integration. Okay, and because these are definite integrals, unlike with indefinite integrals, there is no vector constant of integration, vector c, needed. Okay, but that's really it. That is how we integrate indefinite and definite integrals of vector functions. Now the only thing left to do is actually take a look at some examples of integrating some vector functions. And when we go to do that, all of the integration rules and methods from Calc 1 and Calc 2 are in play here. All right, so that includes your very basic integration rules, u-substitution, integration by parts, trig substitution, whatever. All of the integration techniques that you have learned in the past are applicable here. And so if it's been a while since you've used some of those integration techniques, if you don't remember them at all, I would encourage you to go back and review them. But if you just need a little refresher, no worries. I'm going to go through a couple examples here with the intention of jogging your memory on some of these integration techniques that maybe you haven't used in a little while. But I think once you see them again, it'll come back to you. All right, so while we technically are doing something new here with integrating vector functions, I'm also going to use these examples to help you review some of your integration techniques, okay? Because you are going to be using them a lot throughout Calculus 3. But enough about that, let's take a look at our first example. First up, we have this integral. It is an indefinite integral because there are no bounds of integration, so we will have a vector constant of integration. In particular, we are integrating this vector function, t cubed I plus t squared j plus tk, all multiplied by dt. All right, so if we want to integrate this vector function, what we need to do is integrate each of the components individually. Now, if the components get pretty complicated, which they will in some of our later examples, I would recommend that you write out each integral individually, solve them, and then put the pieces back together to form your antiderivative of the vector function. But in this case, we have three very simple functions to integrate, so I'm just going to keep them all in one line here. All right, so what we're going to have here is the integral of t cubed dt, and that will be multiplied by I. Then we'll have the integral of t squared dt, and that's all multiplied by j. And then we have the integral of t dt times k. All right, we're taking the integral of each component individually. This is the integral of the x component, this is the integral of the y component, and this is the integral of the z component. And so now we just have to solve each of these indefinite integrals. And in each case for these three integrals, we are going to be using the most basic integration rule, which is the power rule for integration. You want to add 1 to the exponent and then divide by that new exponent. So this will be equal to t to the 4th power divided by 4, and that's multiplied by I. Then we will have t cubed divided by 3, and that's multiplied by j. And then we have t squared divided by 2 times k. All right, you just add 1 to each of those exponents and divide by that new exponent. Now we're not quite done yet. We did forget one thing, and that is the vector constant of integration. We can simply tack that on to the end here. I'm going to write plus c. Okay, so there's no need to write out all three constants of integration from each of these integrals and then group them into the vector constant of integration. You can skip all that work. I showed it to you at the beginning of this video so that you know why we can just write plus vector c. You don't have to do that work every single time. You can just integrate all three of your components individually and then add on that vector constant. Okay, but that's it. That would be the answer to the indefinite integral of this vector function. Let's take a look at another example. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful, then I'd invite you to join my membership site JK Math Plus, where you get access to many perks including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I will have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. Here we have another indefinite integral, specifically the integral of this vector function with components of cosine t, negative sine t, and secant squared t. All right, so if we integrate this vector function, we will have the integral of cosine t dt times I minus the integral of sine t dt times j plus the integral of secant squared t dt times k. All right, this is the integral of the x component, this is the integral of the y component, and this is the integral of the z component. Now we just have to solve each indefinite integral. Starting with the first one here, the integral of cosine, that's one of our very basic trigonometric integration rules. We know that the integral of cosine is sine, so this is equal to sine t times I. Then for the integral of sine, we know that that is negative cosine. So the integral here will be negative cosine, but this negative out front will cancel out with that. So we do get plus cosine t times j. All right, do not forget your negative signs for some of these trig rules. Remember that the integral of sine is negative cosine. All right, but then moving on to our last component, we have the integral of secant squared t. Remember that that is just tangent because the derivative of tangent is secant squared. All right, so we will have tangent t times k. And then once again, don't forget your vector constant of integration. I'm going to add plus vector c on the end of my answer there. And that's it. That would be the answer to this indefinite integral. Pretty simple, not too difficult, but it is a good refresher on some of your trig rules for integration that will come up fairly often throughout this course. All right, let's take a look at another example. This time we have another indefinite integral, but our vector function has components of e to the power of t, 1 divided by t, and the square root of t. Okay, so if we integrate, we will have the integral of e to the power of t dt times I plus the integral of 1 divided by t dt times j plus the integral of the square root of t dt times k. All right, this is the integral of the x component, this is the integral of the y component, and this is the integral of the z component. All right, now let's start with the first integral here. This is probably the easiest integral you will ever solve. Remember that the integral of e to the power of t is just itself. So this is going to be equal to e to the power of t times I. Then let's move on to the next integral. We have the integral of 1 divided by t. Remember that this will require the use of the log rule of integration, specifically the natural log. We know that the integral of 1 divided by t will be the natural log of the absolute value of t. All right, so we'll have the natural log of the absolute value of t times j. And then finally, for our last integral, we have the integral of the square root of t. It's not initially clear how we can integrate that, unless you have it memorized, but what we want to do here to see what rule we would use is to rewrite the square root as a 1/2 power. So what I'm going to do here is rewrite the square root of t as t to the 1/2 power, and then you can see how to use the power rule of integration here. You'll add 1 to the exponent and divide by that new exponent. So 1/2 plus 1 is 3/2. So we will have t to the 3/2 power, and then we're going to divide by 3/2. But remember that dividing by a fraction is the same as multiplying by the reciprocal of that fraction. So I'm just going to multiply by 2/3, all right? That just looks nicer to me, so that's how I'm going to write that. And don't forget that that is multiplied by k. And then you want to add on your vector constant of integration, and you're done. That right there would be the integral, or the antiderivative, of this vector function. Let's take a look at a little bit more of a difficult integral. For this example, we still have an indefinite integral, but our components are not going to be as easy to integrate as they have been in our first few examples. Our x component is t times sine of t squared, our y component is t times cosine t, and our z component is just tangent t. Now, as I've already said, these are a little bit more involved, so the integrals are not going to be one-step integrals. They're not going to be super quick, and so I am going to take the time to split them up and work on them individually. Here's what I mean by that. Let's start with the integral of the x component. We have the integral of t sine of t squared dt. What we have here is, for one thing, a product of two functions, and we also have a composite function, or sometimes you'll hear it called a nested function, right? We have this t squared inside of the sine function. And so when you have an expression like this, there's a couple different integration rules that you could use. The first one that I would always try to use is u-substitution, and then if that doesn't work, then maybe you want to look to integration by parts or trig substitution or something like that. But in this case, u-substitution is going to work. What you want to look for when using u-substitution is, do you see a function and its derivative? Because you're going to set u equal to the function, and then the u-sub will take care of that derivative. All right, and typically what you set equal to u will be the inside function of a composite function. So in this case, I want to set u equal to t squared, the inside function of sine, because its derivative is also within the integral. The derivative of a t squared function will be a function of t to the first power, which we have right here. Now there might be some constant in front of that, but that's okay. We can deal with constants as long as the variables match up in terms of the derivative. All right, so here's what that's going to look like. I'm going to set u equal to t squared. We'll have du dt equal to 2t. That's the derivative of t squared. And then solving for du gives us du equals 2t dt, and then whatever du is equal to, you want to try to find that in your integral here. Now, I don't see a 2t dt, I just see t dt. So what I'm going to do to adjust for that is divide both sides by 2. So we have du divided by 2 equals t dt. And now we can rewrite our integral in terms of u and integrate. We'll replace t squared with u and replace t dt with du divided by 2. And then everything will be in terms of u, and we can integrate a much simpler integral. All right, so we will get this. We'll have the integral of sine u times du divided by 2. Now you can pull that 1/2 out to the front, and then the integral of sine is negative cosine. So this is equal to negative 1/2 times cosine u. Okay, and then to complete the integral here, you just want to replace u with what we set it equal to, which is t squared. You want to get everything back into terms of t, and so that will give us negative 1/2 times cosine of t squared. Okay, so that is the result of integrating the x component. Now let's move on to the y component. Our integral will look like this. We have the integral of t times cosine t dt. Now, once again, we do have a product of two functions, but there is no composite function or nested function, right? There's really no way for us to use u-substitution to solve this integral. It's just not going to work here. There's no function and its derivative that we can see. So the next thing that I would probably try to do here is use integration by parts, which is particularly useful when you have a product of two different functions. In this case, that would be t and cosine t. And if you remember the formula for integration by parts, it looks like this. The integral of u dv is equal to u times v minus the integral of v du. All right, so we have to choose something to set equal to u in this integral and something to set equal to dv. The way that I like to go about it is I like to think of what gets simpler when I take its derivative, and I'll set that equal to u, because what you're going to do is take the derivative of whatever you set equal to u. In this case, t gets simpler, right? You take the derivative of t, you just get 1, as opposed to cosine, whose derivative is negative sine. That doesn't get any simpler, it just becomes another trig function. So what I'm going to do is set u equal to t and set dv equal to everything else, which in this case is cosine t dt. And then what I'll do is differentiate u and integrate dv. So we will have du dt equals 1. 1 is the derivative of t. And then solving for du, we get du equals dt. Now, on the other hand, we are integrating dv, so we will be integrating cosine t dt. The integral of dv is v, and the integral of cosine t is sine t. All right, so we get sine t. And so now we have everything we need to rewrite this integral using the integration by parts formula that will then give us a simpler integral that we can actually solve. Okay, so this will be equal to u times v, so we have t times sine t, so I'll write t times sine t, and then we're subtracting the integral of v du. V is sine t, du is dt, so we have the integral of sine t dt. And so hopefully you can agree that using this integration by parts formula made this integral easier to solve. The integral of sine t we know is negative cosine t, so we get t sine t minus negative cosine t, but of course those two negatives cancel out, So the result is t sine t plus cosine t. All right, that is the integral of our y component. Now finally, let's move on to the integral of the z component. We're going to be taking the integral of tangent t. I'm going to do that one up here. It's a little bit easier than the last two, but it does require that you remember a specific integration rule. The integral of tangent is not as simple as the integral of sine or cosine. Instead, you have to remember one of the other trig rules for integration that involves a natural log function. Specifically, the rule is this: the integral of tangent is equal to the negative natural log of the absolute value of cosine t. All right, hopefully that looks familiar. If not, feel free to go back to Calculus 1 and review your integration rules. Otherwise, I am going to move on here. We now have integrated all three of the components of the vector function in this indefinite integral. Now we just have to piece them all back together. We want to have the integral of our x component times I, plus the integral of our y component times j, plus the integral of our z component times k. All right, so our final answer here will be negative 1/2 cosine of t squared times I plus t times sine t plus cosine t times j, and it is important that you remember those parentheses around both of those terms because both of them are being multiplied by j. Both of those terms resulted from the integration of the y component. But then finally, don't forget to add on the z component, which in this case is negative, so I will write minus the natural log of the absolute value of cosine t and then multiply that by k. All right, and then one more thing, do not forget your vector constant of integration. So I'll put that plus vector c on the end, and we're good to go. That is the integral of this vector function. Okay, so I hope this example was a good demonstration of the variety of integration techniques that you were expected to know how to use by this point. You want to know how to use u-substitution, you want to know how to use integration by parts, and you want to know your other integration rules as well, such as the rules that involve natural log functions. Now, by this point in calculus, especially in calculus 3, you might be allowed to use integration tables, which are just tables full of forms of common integrals and their answers. And so if you are allowed to use one of those, feel free to do that. You can skip a lot of this work if you use integration tables, but I'm never going to assume that you are allowed to use those. So when we do solve integrals in calculus 3, I am usually going to show you the process of getting to the answer using integration techniques. Okay, so I just want to make that clear here. If you are allowed to use an integration table, feel free to do that, but I am going to show you all the steps regardless. Okay, but moving on, let's take a look at a definite integral. Here we have the definite integral from 0 to 2 of this vector function. It has components of t, e to the power of t, and negative t times e to the power of t. Okay, so now since this is a definite integral, I am going to split up the work here and then piece it back together. I'm going to integrate each of these components individually and evaluate them from 0 to 2, and then we will combine our results at the end. So let's start with the x component. This one's pretty simple. We're going to be integrating t from 0 to 2, and so the integral of t is just t squared divided by 2. So this is equal to t squared divided by 2, evaluated from 0 to 2. And then plugging in 2 squared is 4, divided by 2 is 2. And then you're going to be subtracting, plugging in 0, but 0 squared is 0, divided by 2 is 0. So this is just equal to 2. All right, then for the integral of the y component, we have the integral of e to the power of t dt from 0 to 2. The integral of e to the power of t is just itself. So this is equal to e to the power of t, evaluated from 0 to 2. Plugging in 2, we get e to the power of 2, and then we're subtracting e to the power of 0. And anything to the power of 0 is 1. So this is equal to e squared minus 1. All right, and then finally, let's take a look at the z component. This one is the most involved out of the three integrals here. I'm going to keep that negative on the outside and write the integral like this. We'll have the negative integral from 0 to 2 of t times e to the power of t dt. And this integral is not as simple. we're actually going to need to use integration by parts here because we have a product of two functions that we really can't integrate otherwise. U-substitution is not going to work here. There is no function and its derivative, but we do have a product of two parts that can easily be integrated using integration by parts. All right, so once again, don't forget, integration by parts says that the integral of u dv equals u times v minus the integral of v du. So in this case, I'm going to set u equal to t because t gets simpler. When you take its derivative, it becomes 1. So we'll have u equals t, and then I'll set dv equal to everything else, which is e to the power of t dt. And so taking the derivative of u, we get du dt equals 1, so du equals dt, and then we're integrating dv, so we integrate e to the power of t dt, and we get v equals e to the power of t, right? The integral of e to the power of t is just itself. So putting all those pieces together, we get this. We will have negative, and then we're going to rewrite our integral using the integration by parts formula. uv will be t times e to the power of t, so we have t times e to the power of t minus the integral of v du. So we have e to the power of t dt. So e to the power of t dt, and then the integral of e to the power of t is just itself once again. So distributing that negative, we get negative t times e to the power of t plus e to the power of t. Okay, now don't forget that this is a definite integral. So let me put those brackets in here. We are evaluating from 0 to 2. And so now let's actually do the evaluation here. Plugging in 2 will give us negative 2 times e squared plus e squared. And then we will subtract negative 0 times e to the power of 0 plus e to the power of 0. And so simplifying, if we have negative 2 e squared plus e squared, that will just become negative e squared. And then this term is 0. 0 times e to the power of 0 is just 0. And then e to the power of 0 is 1. So this just turns out to be 1, but we're subtracting it, so we have minus 1. Okay, and if you want, you could pull out negative 1 here, or just pull out that negative and get negative e squared plus 1. All right, and so now putting all of that together, we will get this. The definite integral from 0 to 2 of this vector function is the integral of the x component, which is 2. So we have 2 times I plus the integral of the y component, which was e squared minus 1. So we have e squared minus 1 times j. Don't forget those parentheses. And then you want to add on the integral of the z component, which was negative e squared plus 1. So we'll have minus e squared plus 1 and multiply that by k. All right, and that is the final answer. It looks a little weird at first because usually when we evaluate definite integrals, we just get a single constant value. But remember that we are integrating a vector function here, so our result is going to be a vector. There's no t's in any of the components of this vector. You could think of it as a constant vector. All the components are constant, but regardless, it is a vector and it is the result of this definite integral. Okay, now before we close out this lesson, there is one more thing that I want to talk about, and that is initial value problems. Just like we did in Calculus 1, we can find particular solutions to indefinite integrals given an initial value. In other words, we can solve for that vector constant of integration c if we are given some information about our desired result, right? So for example, here we want to find the vector function r of t that satisfies the initial condition. And we are given the derivative of that vector function, so integrating it will take us back to the original vector function. And for that derivative vector, we are also given an initial condition. We are told that when we plug 1 into that original vector function, we should get this vector, I plus j plus k. All three components should be equal to 1. All right, and so the process is very similar. It's almost exactly the same to how you solve initial value problems in Calculus 1. We will integrate the vector function as normal. Remember to include that vector constant of integration, and then we will use the initial condition to solve for that vector constant of integration. All right, and that will give us the particular solution to our indefinite integral for the given initial condition. All right, so let's work on this here. We want to find the vector function r of t, and we will do that by integrating r prime of t. All right, so what we want to do is integrate each of the components individually of that vector function. So that will look like this. We will have the integral of 3 dt times I plus the integral of 4t dt times j plus the integral of negative 9t squared dt times k. This is the integral of the x component, this is the integral of the y component, and this is the integral of the z component. So now solving each of these indefinite integrals will give us this. The integral of 3 is going to be 3t, so we have 3t times I plus the integral of 4t dt. We'll add 1 to the exponent and divide by that new exponent. So we'll have t squared, and we're dividing by 2, so that 4 will become 2. We'll have 2t squared times j. And then finally, for this integral, we will use the power rule of integration again. Add 1 to the power, so we'll have t cubed, and then divide by 3. Negative 9 divided by 3 is negative 3. So we'll have minus 3 t cubed times k. And then don't forget your constant of integration, or the vector constant of integration, c. All right, so in our previous examples for indefinite integrals, we would be done, right? This is where we stopped. We found the general solution to our indefinite integral, but now in this case, we can actually find a particular solution because we know that when t is equal to 1, or when we plug 1 into the vector function, this is what we get. All right, so what we found here is the vector r of t, because we integrated its derivative. When you integrate a derivative, you get back to the original function. So we can now plug 1 into this result and set it equal to what we know it should be equal to. When we plug in 1, we should get I plus j plus k. So I'm going to set I plus j plus k equal to this vector function evaluated at 1. So we'll have 3 times 1 times I plus 2 times 1 squared times j minus 3 times 1 cubed times k plus c. All right, 3 times 1 is 3, 2 times 1 squared is 2, and negative 3 times 1 cubed is still negative 3. So continuing our work over here, we have I plus j plus k equals 3i plus 2j minus 3k, and then plus c. Now what we have to do to solve for c is subtract all of these terms over to the other side. In other words, we're going to be combining our like terms for the x, y, and z components. We'll subtract 3i from I, and that will give us negative 2i. Then we will subtract 2j from both sides of the equation. So j minus 2j is just negative j, so we have minus j. And then we'll subtract, or in this case, add 3k to both sides of the equation, and k plus 3k is 4k. So we have plus 4k, and now that is equal to c. And so what we found here is the constant vector that c is equal to, right? All three of these components are constants, negative 2, negative 1, and 4. And so this is what this c right here would be in our answer to this indefinite integral. We can now fully write out the particular solution. We can replace this c with this vector that we just found by using the initial condition that we were given. So let's do that. What I'm going to do is just simply rewrite our vector function down here. R of t will be equal to 3ti plus 2t squared times j minus 3t cubed times k, but now we're going to add that constant vector that we just found. It's a negative 2i minus j plus 4k. So instead of writing a plus sign here, I am going to write minus 2i minus j plus 4k. Now, I suppose you could leave it in this form, but that's not really the simplest form. We could actually make this vector function look a lot nicer by combining our like terms, or combining the x, y, and z components of the two vectors, right? We can combine this vector with our constant vector. We can combine the x components of 3t and negative 2. We can combine the y components of 2t squared and negative 1. And we can combine the z components of negative 3t cubed and 4. And so putting that all together gives us our final answer that our vector function r of t is equal to 3t minus 2 times I plus 2t squared minus 1 times j plus the z component, which would be negative 3t cubed plus 4. But to make it look nicer, I'm going to put the positive value first. So we'll have 4 minus 3t cubed. All right, so we have 4 minus 3t cubed times k. And that right there is the final answer to this example. We have found the vector function r of t from its derivative r prime of t that satisfies the initial condition that we were given. Okay, so that's how you can go about initial value problems involving vector functions. All you want to do is integrate your vector function as normal, and then once you get to the point where you have that constant of integration plus c, you want to use that initial condition that you were given, solve for c, and then plug it back into your general solution, and then simplify it to get your particular solution. Okay, and if you wanted to check your answer, if you wanted to see if this is correct, we do know that r of 1 should be equal to I plus j plus k, so you can plug 1 into your answer here and see if you get that vector. In this case, you will. 3 times 1 is 3, minus 2 is 1, so you do have 1i. Then 2 times t squared, you'll have 1 squared, so you'll have 2 minus 1, which is also 1, and then you'll have 4 minus 3 times t cubed. Well, 1 cubed is 1, so you have 4 minus 3, which is just 1. Okay, so that does check out. Our answer here is clearly the right answer based on this initial condition. Okay, and so with that, that is it for this lesson. That is how we integrate vector-valued functions. If you want to see some more examples, feel free to check out my examples video that I'll have linked here on the screen. If you have any questions, please let me know in the comments. But if you don't have any questions, then this is all I had for now. So I will see you next time.